Hello everybody, and thank you for joining me at this lunchtime on day 2 of NAB 2022. So my name's Kevin Salvidge. I'm the Sales Engineering Manager for Leader, based in London in the UK. And today we're going to talk about pipes and now packets, what you really need to know about QC and maintenance of IP. So, you've done it. After all that planning, all that thinking, all of those sleepless nights, you've put together an IP infrastructure. But now, those system designers have left, the consultants have left, the hired engineers have left, you're on your own. Has that training of your broadcast engineers sunk in? Do they understand IP? Are they going to be able to keep this system up and running? Over the next 25 minutes, we're going to touch on some of the subjects that are relevant as you move into this world of IP and you now keep these systems operational. What you have to remember is that IP is just another I/O interface. It's a way of moving audio, video, and data from point A to point B via a switch. It's how we've done that that's changed. We've gone from analog to digital. We're now going to IP. It's just another transition. So although many broadcasters are looking at IP, people are doing this transition at a very different pace. Some are very fortunate. They've got a brand new facility. They can just drop in a complete solution. Others have to migrate. And lots of people are doing this in a piecemeal fashion. So you're having to work with both SDI and IP in live production environments. So with 2110, the timing information has been removed from the underlying hardware layer, making the distribution asynchronous. And with the current broadcast formats, video must be frame synchronous from the camera sensor to the display device, because otherwise television doesn't work. The intermediate IP distribution network is asynchronous, but the variance in packet delivery directly affects latency, leading to potentially longer audio and video delays than we've ever had to encounter with SDI infrastructure. So although uncompressed video such as 2110 does map the active parts of SDI, we have two major challenges. Firstly, we now have a new reference called PTP. So we've got black and burst, tri-level sync and PTP, and they may not be in the same reference generating device. And as I previously mentioned, you've got signal distribution in IP. It's asynchronous and it's multiplexed. So let's take a look at SDI transmission. In SDI, we sent video, audio, and data all in the same coax cable, line by line. We sent a field or frame of video, the audio that goes with each field or frame, and the ancillary data that travels with it. Now, our industry is naturally conservative, so our first move into the world of IP, using 2022-6, saw us replicate SDI in a single RTP flow and use UDP and unicast protocols. So in simplistic terms, all we did was change the transport mechanism. Now, with 2110, we send audio, video, and data in 3 different IP multicast streams, frequently referred to as essences. And these different streams can be on the same fiber, but they don't have to be. And they're moved under 3 different parts of the SMPTE 2110 standard. So -20, active video, -30, audio, and -40, ancillary data. And each of those parts of the standard are broken down into subsections. So here you can see 2110 uses separate video, audio, and ancillary data essences. And it uses RTP and UDP. It uses PTP for synchronization. This is the IEEE 1588 standard with the SMPTE 2059-2 profile. And these three IP flows, or essences, make up your program and are commonly known as a service. So things we used to do with analog video when we moved to SDI. With analog video, we could hang an oscilloscope on a video coax cable and look at it. We had to come up with a way of looking at SDI, taking that 10-bit stream, making a pixel out of it, and putting that pixel on the screen. With analog audio, we could put a scope on the output and see the waveform that we've got an audio signal. And with SDI, we had to come up with a way of grabbing that information that was placed in the hank so that we could analyze it on a waveform display. Now, we're taking that expertise and we're moving it from SDI to IP. So SDI allowed us to carry audio, captions, and lots of other ancillary data in the video payload. So now we need new tool sets and new ways to look at them. Well, we're having to look at this again in a completely different way. We have to move everything around and put it in IP, but not just IP, but 3 different IP multicast flows. We need to find a way to make new tools that look at video, audio, data, probably captions is the most important that any of you have to deal with, and make sure that the video, audio and captions are compatible with being returned back to SDI if you need to in your facility. And we need to look at how to do this and see IP and SDI side by side. So we have another set of challenges here. Those that are engineers, the tools they need to be able to analyze these networks and see that they're operational, versus the day-to-day production and operational requirements. IP engineers need tools that can deep dive into these IP networks and analyze their performance and their trends, such as IP flow status, packet jitter, PTP timing, buffers, 2022-7, path delay, and there's a lot more. Whereas production, day to day, needs the waveform, vector, the displaying of captions, SCTE 104, audio loudness, and the ability to compare IP to SDI if you've had to go through gateways. So for SDI troubleshooting, you're all familiar with the status, I pattern, jitter, and timing. And these were used to measure the integrity of the SDI signal. Now, with IP, the status display that you and I have grown up with changes. And it becomes much more of a network-centric, carrying information that's important about each service, confirming that we've got the correct protocols, that we've got the correct streams, we're coming from the correct devices, and we've got the correct payload information. And we have to monitor that the links that we're connected to are actually connected and that they're carrying data and that there is no errors on those packets when they arrive with you. And finally, you need to be able to monitor this over a prolonged period. IP networks don't typically fail like that. What they do is they gradually tail off or they peak up. And it's watching trends, and that's where test and measurement equipment becomes vital within your organizations for viewing these trends over extended periods. This could be 24, 46, 72 hours. We also have now the challenge that the timing's been removed and we're putting it over networks that we have no control on. So we get jitter introduced. And the way we look at this is by monitoring what's known as the inter-packet arrival time. Sustained jitter can mean that we have bursts of packets, which means we can flood buffers. The other way, if packets get delayed, you can starve a buffer. And if you've got no information, the device won't be able to play it out. So if packets are excessively bunched, you can overload the system. So you need tools that can show you the performance and how the packets are arriving. You also need the ability to analyze these externally to your test and measurement products. So tools such as being able to download CSV files of all this data is essential. And many of you will be familiar with tools such as PCAP, which allows you to capture data on particular ports, particular types of data like PTP data, then take them away and analyze them in third-party programs like Wireshark. So with 2110, as I said, the timing information has been removed from the underlying hardware, making the distribution asynchronous. Black and burst and tri-level sync's been replaced by precision time protocol. And PTB is time-based, as opposed to the phase-based black and burst and tri-level sync. So many of you would have seen the diagram on the right, and this details how the timing is worked out between the grandmaster and the follower by sending messages, time-stamped when they're received, comparing the timestamp and sending it back. And this allows us to display graphs that show delay time and offset time. And I'll use an example here. You finish work early, last meeting 2 o'clock on Friday, you jump in your car, you get on the freeway, there's no traffic, you sail home, you get there, you're not stressed, there's no trouble at all. However, the meeting overruns, you're still in the office at 5:30, you get out by 6, you jump in your car, the freeway is gridlocked, you're just sat in it. That's like networks. There's too much traffic going through them, it's slow, it's unreliable. So you decide to get off the freeway at the exit ramp, you go up, over the top and come back the other way and there's no traffic, and you move freely. So these are the things you need to look at with networks and timing. Is the traffic lumpy going one way, but it's flowing freely coming the other? Because we're looking at multiplex signals here. So these tools allow you to see kind of that activity and that traffic that's going on your networks. And the display synchronization, status time and information is critical. You need to make sure that you are looking at the correct grandmaster on your network. You've designed this system, you've designed it with failover, so should something fail, it cascades to the next one you expect. Is it doing it? So you need tools that can confirm you're looking at the correct grandmaster, that you're looking at the correct PTP domain. In complex systems, you may have multiple domains. You may have a PTP video domain, you may have a PTP audio domain. And you've got to be able to look at the traffic, as I mentioned, in real time, looking at the traffic that's being sent one way through the switch and coming back the other way. And also make sure that the frequency of those messages is being sent at the intervals you expect, so you can analyze and monitor the performance of your network. And again, having a graph that displays this information is absolutely critical. So once we're confident that our PTP reference is stable, we can start to investigate the timing on each of the 2110 multicast flows. With SMPTE 2110-20, only the active pixels are being streamed, which brings with it a new series of measurement challenges. So from an SDI perspective, you'll all be familiar with this type of graphic with the crosshair, your black and burst, and your signal normally sitting perfectly in the middle. And we start at line 0, pixel 0. But in the world of IP, we don't. The marker bit, which is like the end of active video, you'll see this. So if you don't see a marker bit, you don't know when the end of that active video is. and that can cause you lots of issues. So, remember, dash 20 is active pixels only, so we start here. And for interlace signals, that will be a 21 line offset. If you're using progressive, it can be 42, 43 lines. So here you can see on my display, it clearly states that my vertical phase offset is 21 lines, and that corresponds with an interlaced image. I'm just looking at video there. Remember that we've got audio and we've got ancillary data. So you need tools that allow you to view both the video, audio and ancillary data and their PTP to RTP timestamp timing to make sure your system's working correctly. So you'll notice here that my total phase offset is 610 microseconds, and it also appears in the display on the right. So you've got ways of correlating that your system is correct. Because we're also moving just the active video, we have to look at, in the analog world, what we call start of active video. And that's known as the first packet arrival time. And again, you need tools to confirm that the first packet is arriving within the window of the standard that you're working to. And again, graphs like these allow you to confirm that here the total phase is 692 microseconds, and on the right you've got confirmation there from the first packet arrival time graph, so that you know your system is working as you expect. So if the timing comparison display and the first packet arrival graph are outside the expected window range and no image is being displayed, there's one further test you can deploy. And on the leader products, we have a mode where you can switch the timestamp mode off. And what do I mean by that? In this mode, the test and measurement device will lock to the first packet. So this is the equivalent in SDI of switching off your black and burst reference. You've got a reference, but you've got no picture. You take the black and burst off and you use the video as the reference. It means that the signal is correct, but it's completely timed wrong. So you've got to find out from the sender, why is it wrong? Why is it outside of the window you can't see? So here is a way of verifying that you've got an image, but you've got a timing issue related to that image. And you can leave the test and measurement device in this mode, but other devices on the IP network might not lock to that signal. So if I'm not locking to it as a test and measurement product, you can guarantee other products are not going to see this and you've got problems on your network. So IP troubleshooting. In the world of SDI, we had CRC errors. We're all familiar with them, the bane of our life, chasing our tail trying to find them. In the world of IP, we have what are known as RTP errors. And these are quite important because this is like the MPEG transport stream continuity count. CRC errors will not pass through an IP switch. It will throw the packets away. And if they pass through the switch, they may lead to unexpected changes and corruptions in your stream. It could be just a bit flipping, but it could mean the channel that you're watching is completely changed. So looking out for these is absolutely critical. And if you've got these, you've got to trace them down, find out what's causing them and remove them, because otherwise they could impact your system quite significantly. And when we come to the event log, we've got a whole new language of errors. Look at them. All related to PTP. Completely different language set. And you need test and measurement tools that can capture these, report when they happen, so that you can dive in and start to analyze your network in further detail. So in the SDI world, the video frame rate and resolution information was carried as part of the VPID. Now we just have active video. We don't actually have any information to tell us what resolution it is, what frame rate. That's part of something else. So fortunately, on products like the leader waveform monitors, it will actually display this. Because the video frame rate and sampling rate are determined by the packet arrival time and the RTP timestamp. So this will start to allow you to confirm that the video is the resolution you're expecting. It's the frame rate you're expecting. I've only got 25 minutes today. I'm not going to talk about session description protocol files. That's a whole other game. But that is another area where you'll have problems. And at Leader, we're looking to do a follow-up presentation that talks about the challenges of SDP, errors in them, and how it can affect the operation of your system. Ideally, you're going to need a test and measurement tool that you can configure the layout so that you can see all of the parameters of your IP network. The traditional single screen or quad split display just don't work anymore in the world of IP. Here you can see I've aligned using the customizable layout. I've got the status page, I've got my packet arrival, I've got my PTP, and I've got at the bottom there another chart, one of the timing. And this allows me to look up and down the graph so that I can see what's going on with the packets arriving, with the PTP, with my timing, making it easy to identify when an error occurs. Yet on the left-hand side, I've got the tools that we're always familiar with from the world of SDI. I've got a picture, I've got a waveform, I've got a timing chart. I could have audio in there as well. So every device may show the errors in a picture a little differently. It all depends on how the picture is built. In 1080i, one IP packet is about 1/4 of a line. That's how much data will be lost for one packet error. Some packet pictures are going to break up randomly. Some are going to have lines on them. And some might just be completely black. So a sliced picture basically looks like SDI in UHD, a quad split that's gone horribly wrong. And you can see here the picture has been sliced and misaligned because the TRS messages are in the wrong place and it's got completely confused. You could have a pretty nasty picture with horrible lines on it. Or, in the worst case scenario, stuff like that. So, we've established that our IP network is operating correctly. We now need a suite of analysis tools for that day-to-day production that operate in both IP and SDI infrastructures. Remember, IP is just another I/O interface. It's how we analyze it. For day-to-day operations, you're going to need tools that are able to look at the image. Camera shaders don't care if you're SDI or IP. Their job is to make sure the cameras match, and they use tools like the picture, waveform, and vector. They don't care if some of those are SDI or some are IP. And products like the Leader Zen series allow you to operate in true hybrid operation. So you can display both IP and SDI sources simultaneously side by side. This is essential if you've got gateway products that are taking your signals from SDI to IP, IP to SDI, because the gateway products are good. Where we see most of the challenge is that you're going from a black and burst reference to a PTP reference that may not be, again, from the same device or may not be correctly timed. Day-to-day operations, here's a very traditional quad split display, and the same applies. They look extremely similar, but it's only when you look at the status display that you see the difference. SDI against IP. And again, it's basic tools like the waveform with confidence that you've got the picture. One is SDI, one is IP. They're tools, they are displayed like your production and operational staff are familiar with today. But probably the real challenge comes with the ancillary data. And in true hybrid operation, I can see here that on SDI, I've got my captions, but on my IP stream, captions are not there. And I can use multiple tools, including picture and waveform, to display and allow me to start to fault find. And this applies also for audio as well. So here, I can put the two side by side, my SDI embedded audio and my Dash 30 stream, and I can see that channels 5 and 6 are missing, my surround sound channels. And also, if you go into the VPID information, many people refer to this as the magic decoder ring. If you've tried to work out the byte references of the 4 bytes that make up resolution, frame rate, aspect ratio, color imagery, you need tools that can display them both in SDI and highlight that they're different in IP. So you've got to remember that IP is just another I/O interface. It's how we analyze it. IP networks don't typically drop off cliffs and fail. They gradually drift. So having test and measurement tools that provide you with the ability to monitor over a prolonged period of time is vital. You need tools that still show you errors that you can relate back to SDI video, and showing SDI and IP side by side. And you need timing tools to verify your SDI and IP are locked to the same clocks. And you need simple user configurable multi-viewer displays. The traditional quad split display is no longer good enough for you to analyze all these tools simultaneously. If you want more information, LEADER have been working with AIMS as part of the education working group. So we'd like to promote this as being a repository for a lot of IP information. If you have any questions, I'm Kevin Salvidge. I'm based in Europe. My colleague Steve Holmes covers the Americas, and our contact details are there. And if you'd like a copy of this presentation, hit that link now and register your details. Simply enter your name and your email address, and we'll get back to you with where you can download the presentation. I'd like to thank you all for joining me, and enjoy the rest of NAB 2022. Thank you.
Thank you, Kevin.